All right, let's go and get started by taking a look at page 6. And we'll look at the homework that you had, numbers 1, 2, and 3. You were given two sides of a right triangle. And you were, first of all, going to have to find the third side. Then you were supposed to find both the sine, cosine, tangent of angle A and of angle B in each case. So given that side A is 3, side B is 4, which side of the triangle do we not know, Ethan?
The hypotenuse.
The hypotenuse, side C. So to find it, we have to use the Pythagorean theorem. And what would side C be using the Pythagorean theorem? Jamie?
5.
5. All right, so we can draw a triangle, and we can label the hypotenuse as 5. We can label one leg as 4. We can label the other leg as 3. We need to realize, though, the 3 is leg A. The 4 is leg B. Therefore, this angle across from the 3 is angle A, or vertex A. Across from side B is angle B, and of course across from side C is the right angle C. Did you get your picture correct? Check your picture.
Mine's backwards, but I'm 100% sure I still got the right answers because the numbers still match up with the correct letters. It's just like my B is on the bottom and not on the top.
But B is across from the 4.
Correct.
Okay, as long as B is across from the 4, A is across from the 3, and C is across from the 5. So your picture is correct?
I guess.
You're good, you're good. All right, so we want to find the sine of angle A, the cosine of angle A, the tangent of angle A, and we want to find the sine of angle B, the cosine of angle B, and the tangent of angle B. And as we find sine, cosine, tangent, there is a phrase that needs to be in our minds. What is that phrase, class?
Sokatoa.
All right, very good expression there, Chris. And I heard a mumble from the rest of you, except for Ethan. I don't think I heard Ethan. Ethan, what's that phrase?
Sokatoa.
Not nearly the expression, but
Sokatoa.
Sokatoa.
I heard it sound like a weird.
The main thing is, I don't care.
I don't care.
Come on, Ethan. Sound like a weirdo. Sokatoa.
Sokatoa.
There we go. See, yeah. See, you gotta, okay, so I used to be like super concerned with what people thought of me until about my junior year. And about junior year, I was like, I really don't care.
Yeah.
Man, I had so much more fun in life, and I just didn't care. Goofy, I don't care what people think. All right, how do we spell Sokatoa, though?
SOACAHNTOA.
If you misspell it, it doesn't help you. So now again, normally I won't write it out, but it's not a problem for me to write it out. I at least think Sokatoa, and I picture the words in my mind, or at least whatever word I need. I say word. Whatever set of 3 letters I need. To help me remember, class, that sine is opposite over hypotenuse. Cosine is
Adjacent hypotenuse.
over hypotenuse. And then tangent is
Opposite over adjacent.
All right, so for A, the opposite is 3, the hypotenuse is 5, so the sine of angle A is 3 to 5. The cosine, adjacent over hypotenuse, adjacent is 4, hypotenuse 5, 4 to 5. Tangent of angle A, opposite over adjacent, opposite's 4, adjacent's 3, adjacent's 4, 3 to 4. How many of the sine, cosine, tangent of angle A correct? All right, then for angle B, we need to find the sine of angle B to be what, Quentin?
45.
The cosine of angle B, Chris?
3 to 5.
And the tangent of angle B, Jamie?
4 to 3.
Do y'all notice any thing?
Yes.
What do we notice about
They're
these?
pretty much all the same except 4 to 3 and 3 to 4.
The sine and cosine.
Yeah, these two just kind of flip-flop each other, and then these two match.
Does that happen every time?
Interesting. Well, let's see. Let's do another triangle. Let's see if that is a pattern that holds true, or if it's just kind of because these were like 3, 4, and 5 are such nice, easy numbers. Maybe that's all it is. It does. All right, so Chris is going to try to do a spoiler on us here. Let's suppose we got B is 9, C is 15. Obviously, which side are we missing here, Jamie?
We're missing the A.
Side A. We use the Pythagorean theorem to find the legs. We don't square them and add them and take the square root. We square them, subtract them, and take the square root to get 12. And so when we draw our triangle here, we've got a side of 9, a side of 12, a side of 15, a side of bacon. I don't know why. And so angle C should be across from the 15. Angle A should be across from the 12. And angle B should be across from the 9. Did we get our picture set up correctly? Check your picture.
Now I did label like A and B and C for mine. I did like the little Greek letters. I was not sure which one.
Okay, well, because they said to find the sine, cosine, tangent of acute angles A and B, that's why we really needed this. Plus, it helped us practice labeling. Does it make sense at least? Okay. So when we find the sine of A, Jamie, what should it be?
The sine of A, it would be 12 over, wait a minute, yeah, 12 over 15.
Good. Opposite over hypotenuse, 12 to 15. However, we do want to make sure that we class reduce. So we'll reduce it, Jamie, to get.
4 or 5.
Oh wait, these are the same numbers we had last time.
Yeah.
Oh, interesting. All right, cosine of angle A. Quentin.
3 to 5.
Right, 9 adjacent to 15 hypotenuse, which reduces to 3 to 5. And then for the tangent of angle A, Chris.
4 to 3.
4 to 3. So, I don't know if this is going to be a good example because it really is the same numbers again. So we're still dealing with a 3, 4, 5. Maybe that proves nothing. For the sine of angle B, Ethan, what would we get? So, kadon.
Opposite over adjacent.
Ooh, so? So. So.
9 over 15.
There we go. Opposite over hypotenuse is 9 to 15, which reduces to 3 to 5. Well, there's that thing we saw last time with these same numbers. For the cosine of B then, class, probably it's going to be 4 to 5. And in fact, adjacent over hypotenuse does reduce down to 4 to 5. And last time we saw it flip, same numbers, so probably 3 to 4. Yeah, opposite over hypotenuse, 9 to 12 does reduce to 3 to 4. Did we get these answers correct for the second one? All right. Oh, good. Different numbers this time. So let's go with number 3, and maybe this will actually lead one way or the other as far as some sort of conclusion. Or in Chris's case, contusion. It's coming. B is 20, C is 29. Again, we're missing which side, Chris? A. And to find side A, again, square them, subtract them, take the square root. What do we get for side A? 21. All right, these numbers are not going to reduce down to 3, 4, and 5 like last time. We've got almost equal legs and a hypotenuse. So it's almost 45, 45, 90, but one of them is slightly smaller than the other. Of course, the hypotenuse is the longer one. Across from the 20, we've got to put the B. Across from the 21, got to put the A. And across from the 29, of course, we put the C. Check your picture. Did you get it? All right, so for the sine of angle A, what would we get, Jamie?
Is it 20 to 29?
What is sine?
Sine. Sine is opposite over hypotenuse.
All right, so looking at angle A, opposite over hypotenuse.
21 to 29.
21 to 29, all right. What about the cosine of angle A? Quentin?
20 to 29.
Adjacent over hypotenuse, 20 to 29. And for the tangent, Chris? Opposite over adjacent, 21 to 20.
Because I feel like it should have reduced, but it just didn't.
It doesn't reduce at all, does it? For the sine of angle B, Ethan?
20 over 29.
All right, we're focusing on this angle now. Opposite over hypotenuse, 20 to 29. And sure enough, it's matching up for the cosine of angle B, Jamie.
21 to 29.
Right, adjacent over hypotenuse, 21 to 29. Okay, that's what we were thinking would probably happen based on our observation of patterns. And then for the tangent of angle B, Quentin?
20 to 21.
20 to 21, opposite over adjacent. Sure enough, it just flip-flops the tangent, which makes sense because what is adjacent to one angle must be opposite to the other. And that which is adjacent to the other must be opposite to the one. The hypotenuse never moves. So it makes sense then that those would work out that way. Questions on this?
So my hypothesis is now a theory.
It is now established by multiple verifications. We'll actually explain why this has to work, but again,
I'm not original.
No. But I'm glad you noticed. Again, I've said to my wife before, I've said to students before, the biggest obstacle in math is observing patterns. Once you observe patterns, the doors of math open wide to, number one, shortcuts, laziness. It's just the path to the dark side. But noticing number patterns, oh so important, oh so helpful. All right. All right. So let me give you a classwork problem here, and we're going to go back to this Greek letter with the O with the line through it. What is that letter called anyway?
Sine. No, it's the
Theta.
Theta. Very good. Theta. And so we've got this triangle that is unnamed. We've got this angle theta. If I know that this line right here has a length of 10, let's just say 10 inches. Suppose I know that this line here has a length of, let's say, 24 inches. I want you to find the sine of theta, the cosine of theta, and the tangent of theta. Once we've done this, we'll take a look at the rest of your homework from last night. Yes?
I don't have a writing utensil.
The rest of you getting started.
Can I go to my locker and grab a writing utensil? I have them in my locker. I just forgot them. I used it yesterday.
I know.
Well, can we count yesterday? It's just kind of like
No.
it was the second day of school.
No. So you have a quarter, do you buy a pencil, or do you just want to take the demerit?
I think I have $1.
Want to buy 4 pencils?
I can go look. Let me go to my wall.
Okay. Either come back with a pencil, in which case you get the demerit, or come back with $1, in which case I'll give you 4 pencils and a demerit. Look at that writing utensils in his pocket. Now I give you a demerit for disrupting my class unnecessarily. Just kidding.
You run anyway.
Hate to lose a customer.
Yeah.
That's how it's easy.
Pretty much.
Grace Christian School is not supportive of this. Alright, first thing we had to do, Ethan,
Find the hypotenuse.
to be
26.
26 inches. Alright, now, we do need to include inches with this answer, but when it comes to writing sine, cosine, tangent, why don't we need to include inches, Jamie?
Because it'll cancel.
Right, when you make the ratio of inches over inches, it's going to cancel anyway. So what do we get for the sine of theta? Question?
12 to 13.
Well, what does sine mean? Sine's what over what?
Opposite of hypotenuse.
Alright, so for theta, what's the opposite?
10.
10 over hypotenuse, 26. I should have gotten 10 to 26. Again, inches cancel, which reduces to 5 to 13. Does that make sense? All right, what about the cosine of theta, Chris? 12 to 13. 24 to 26, which reduces to 12 to 13. And then back to Ethan for the tangent of theta.
5 over 12.
5 over 12. 10 to 24, opposite over adjacent, reduces to 5 to 12. All right, and we get all 3 correct. All right, and then makes sense here?
Yeah.
So again, don't try to memorize a particular location. Always think opposite, adjacent,
I
hypotenuse.
just switched opposite and adjacent.
Right, but it makes sense why which one's which. All right. Question.
Ha.
Okay. Anyway, let's go ahead and review what we talked about yesterday with the Cartesian plane, that thing that we graph on, and we said that we've got this number line that extends to infinity and extends to negative infinity, and we call this line class the x-axis. This line is the x-axis. Now, if we find the 0 of the x-axis, and we drew a perpendicular number line, one that goes down to negative infinity and up to positive infinity, this line is called class the y-axis. And we'll label the positive end of each axis with x and y respectively. This place, the 0 of both the x and y axes, is referred to as the
Median.
Vertex.
origin. The origin. Make sure that term is in your notes from yesterday, by the way. But I don't know that I even wrote it on the board, so I don't know that you wrote it in your notes. Make sure you got that term down, the origin, particularly if you had forgotten it. And but from there, from the 0, we'll go out 3, 6, 9, and so forth. We'll go up 3, 6, 9, and so forth. We'll go backward, negative 3, negative 6, negative 9. Negative 9 and so forth. We'll go down negative 3, negative 6, negative 9, whatnot. Okay? And so these 2 crisscrossing axes form 4 sections to the graph. We refer to these 4 sections as quadrants. And which is quadrant 1?
Top left.
Top left is quadrant 1.
Top right.
Top right.
So all my answers are wrong.
So where's quadrant 2, Chris?
Top left.
This time it's top left. Quadrant 3 class,
Bottom left.
bottom left. And quadrant 4,
Bottom right.
bottom right. So that it makes a big letter C, if you think about it like that, as opposed to a U or a Zigzag. So it's a big letter C, 1, 2, 3, 4 around this way.
Or square.
And we said that every single point on the Cartesian plane, if we just, I don't know, pick a point at random like this one here, has a particular x value. This point lines up with the 8. So it has an x value of 8. We call the x value of a point, Quentin, the, as he flips back in his notes, Chris?
Abscissa.
The abscissa. He did not have to look back at his notes. To Quentin, since he just saw his notes, what do we call the y value of the point? The ordinate. And when we put those values together, we put the abscissa and the ordinate, which was 6, together in parentheses, separated by a comma. We now have established this point's class coordinates. We have established the coordinates, or the location of the point. And what you did on your homework, page 8, number 3, as you turn there, was to plot the coordinates of some various points. Now, a quick refresher from your algebra days. When you plot a point, my suggestion is start at the origin. Travel however far in the x you need to travel, and then travel however far in the y you need to travel. So if I start here and I'm at the point 5, 2, I'm going to go 5 in the x, 2 in the y. I'll put a dot, and I'll put an A next to it, so I know that that is point A. For B, we should start at the origin class, go back 3 and up 4, and there is point B. For point C, Ethan, we need to start at the origin, go,
-2.
and then
-3.
backward 2 and downward 3 to point C. Jamie, letter D.
Go to the right 2 and down 4.
Good. For -2, 4, right 2, down 4. For letter E, Quentin, the point 3, 0.
Right 3.
Over 3 and up and down, nothing. And there's my point E. Point F, Chris.
Oh, I messed all mine up.
Okay, what do we need to do though on point F? 0, 3.
0 and then up 3.
Good. Over nothing, up 3 to point F. What about letter G, Ethan?
Go down -2.
Good. Just go down 2 to -2. Letter H, Jamie?
Go back -3, then nothing.
Good. At 3, don't go up or down anything. And then I, class?
Nothing.
It's the origin. It's right there, 0, 0. How many had all these points in the correct spots, first of all?
I would have.
You would have. Oh, okay, yeah, sure. Easy to say when you're all talk and no show when you got a homework task. I'm just picking on you. All right, questions.
I know exactly what
I just did it. I just did
did.
opposite lines.
I just missed
Okay.
one.
I did the Y and then the X.
Yeah, I did exactly the same thing I
Okay,
did.
so we remember it now. Graphing has come back to us from our algebra days. All right. Number 7 then builds off of this, and we may need to change our answers a little bit here. It says, in which quadrant do each of the following points lie? And it gives us the point 4, 2. In which quadrant is the point 4, 2? Class?
4.
4.
Over 4 and up 2?
1.
Quadrant 1. How about letter B? -3, 1? Quadrant 2. Back 3 and up 1 puts us in quadrant 2. Letter C, -2, -4?
3.
Oh, backward 2, downward 4 puts us in quadrant 3. Letter D, 1, -3?
4.
4. Forward 1, down 3 puts us in the 4th quadrant. Letter E, 1, 1?
1.
1. Letter F?
2.
2. Letter G?
3.
3. Letter H?
4.
4. It's an insulting pattern. 1, 2, 3, 4, 1, 2, 3, 4.
Must be a
They did
big
that. They did that. All right. All right, questions on that? Let's take a look at number 4. Look back at the previous page, page 8. You don't have to flip anything necessarily, but look at page 8. Number 4 says to form another Cartesian plane on graph paper and graph these points. So, tell you what you could do is maybe if you used a pencil for your homework, get out a pen. If you used a pen for the homework, maybe use pencil so that we don't have to draw another Cartesian plane.
I do.
Or you can just draw another Cartesian plane. I'm going to switch to yellow chalk so I don't have to, and I'll try to carefully erase these other points without destroying my graph grid completely. So either set up a new graph grid or be prepared to switch to another writing utensil so it does these points don't blend in with your homework from earlier.
So when you're graphing this, the dot go on the right side of the box, so it's on
The dot goes on the lines.
on the lines, right? Yeah. Like would it go on, like say it's 4, would it go on the left side of the 4 or the right side of the 4?
This is 4.
Correct.
It goes right here. It doesn't go left or right. It goes right here
I see what you mean.
on the line. It doesn't go in the space. It goes on the line. Unless it's not a perfect point. For instance, like 4.2 would be like just barely to the right of 4. But if it's an integer value for either the abscissa or ordinate, it would be on the line. All right, so number 4 says to form another Cartesian plane on graph paper and then graph these points. So the first point is 3, -4. How do I graph 3, -4, class? Over 3 and down 4. Then it wants us to graph the point 3, -2. What do we do? Over 3 down 2. Then the point 3, -1. Over 3 down 1. And then 3, 0.
Over 3.
Over 3. 3, 1, plot it.
3 up 4.
3, 2, plot it. 3, 3, plot it. 3, 4, plot. Okay, what do you notice about all the points they gave us? Well, they do form a line, but what do we notice about these points? They all have, like if you actually look at the coordinates listed there, what do you notice about every single point? It keeps having
3 is the abscissa.
3 is the abscissa. The x value equals 3 in every case. And if you were to connect these, this point, this point, this point, this point, in fact, every one of these points has an x value of 3. So the equation x equals 3 is this line. Make sense? So what if I wanted to graph x equals -2? What would that look like?
Same thing, it's just on -2.
You go back to -2 and you draw another perfectly vertical line because all these points have an x value of -2. Does that make sense? So when you see the equation x equals blank, you just get a vertical line at that point. So x equals 6.
You go to -6 and draw a straight line.
Well, x equals 6. That's an equal sign. My equal sign was slide. But you go to 6 and draw a vertical line. Make sense? Okay. Look at number 5. Look at number 5.
Why are they doing that?
And look at the points they give you. I'm going to switch to a different color. Not that it's anything really earth-shattering, but you know, why not? Let's go with pink, because Ethan's birthday, and Ethan seems to like pink.
Purple.
Purple. You're a purple guy. Okay, purple chocolate.
Okay.
Some people's kids.
I do not care that it's your birthday and I do not care it's your birthday, I'll go.
All right. So letter A. The point class is 3, -3, -2. I need to start at the origin. Go
Over 3.
back 3 specifically, and
Down 2.
down 2.
And then you do the same like 8 times.
And the next point, no, I don't do the same thing 8 times. The next time I do what?
And then you go over 3.
Nope.
Back.
Backward 2 and downward 2. And then for the next point, what do I do? Back 1 and down 2. And then for the next point,
Down 2.
just down 2. And then over 1, down 2, forward 2, down 2, forward 3, down 2, forward 4. So what do we notice about all these points?
Same pattern.
Same ordinate, right? This time, for every one of these points, it has a y value of -2. And if we connect them, of course, all these points have a y value of -2. So what if I had the equation y equals 5? Go to a y value of 5 and put a horizontal line through 5, right? Or if I had y equals -9,
All with the -9 down.
go to the y value of -9 and put a
Horizontal line.
horizontal line through there.
Did we learn this in algebra 2?
We did.
I think
We're
that's why I
reviewing it
remember
now.
this, yeah.
We're reviewing over it now. Questions on that? All right, look at number 6. I'm going to switch to a pink now. Ethan's former favorite color.
Second favorite. Okay. Blue.
Orange then.
Blue. Orange is good.
All right.
You can't make Ethan
So look at number 6. I know some people. There's no pleasing some people. Number 6. We've got the point -4, -4. So backward 4, downward 4. Then they give us the point -3, -3. Plotting it there on your paper as well. And the point -2, -2. And the point -1, -1. 1, 1. 2, 2. 3, 3. We see what's going on here? Yeah, all of these points form a straight line. But not just a straight line though. A diagonal straight line. But not just a diagonal straight line. A line at exactly what angle?
45 or 80.
A perfect 45-degree angle right here. It bisects the first quadrant and the third quadrant. Now, what do we notice about all the points they gave us?
same numbers?
They're all
The
same.
abscissa and the ordinate always match. They're always equal. So we could say that x equals y for every one of these points. Now, let me ask you this. What if I gave you this equation, though? X equals negative y. What do you think that would look like?
One would be positive. So the abscissa would be positive, and the ordinate would be negative.
Right.
That's it.
So what would that look like if I graphed it?
It would be going
Well,
that way,
that's
not
not
that way.
Okay, so for instance, we said, well, if we go with a 5 for the x, we'd have to go with a negative 5 for the y. But if we went with like a negative 4 for the x, we'd have to go with a positive 4 for the y.
Yeah.
So we'd end up with a
There's a term for this. I forget the name for it.
45-degree angle going the other way, if you will. 45 degrees here, though, right? It'd be perpendicular to the first line, but it'd be bisecting the second and fourth quadrants instead, wouldn't it? Okay, questions on this? Yes, sir.
Is that called like the slope or something?
There is a slope, right? This has negative slope, this has positive
Yeah,
slope.
that's what I was thinking.
This has zero slope, this is undefined slope. So, yeah, all kinds of stuff we talked about in algebra class. All right, good times. All right, questions on this? All right, let's move off of graphing then. Next section of your notes. You put your graph paper away. Reciprocal, I know, now it's just starting to be fun too, and then we pull the plug, even on his birthday. All right, next section of your notes. Reciprocal identities. Reciprocal identities. Reciprocal identities. I want to quickly review this word identity. We talked about it in Algebra 1 and Algebra 2. Anyone remember off the top of their head what an identity is?
The abscissa and the ordinate together.
Has nothing to do with graphing.
Okay, cool.
Amount or something?
No. Obviously, in geometry, identity was that idea that something was equal to itself. In algebra, an identity is a type of equation. And it's an equation that is always true, no matter what your answer is. So, for instance, if I said x plus 1 squared minus 2x is equal to x squared plus 1. I don't care what number you make up, it'll work. This is called an identity. One in which x can equal all real numbers. Plug in a 5, it'll work. Plug in a 7, it'll work. Plug in a negative 3.8498724, it'll work. Anything will work. Because it's what it is, it defines it. How you would simplify an identity, you could square the first, square the last, multiply and double. And of course we see, well, the 2x and negative 2x cancel. Hey, the 1's cancel, the x squared cancel, everything cancels. That's because it all matches. It is itself, right? It's always true. As opposed to like a conditional equation. Okay, remember we said a conditional equation is only true for certain values. Like for instance, if we said x squared minus 3x is equal to, let's say x squared plus 3x is equal to, that wouldn't work either. Let's go with the 15 here. Let's go with the 2x here. X squared plus 2x equals 15. There we go. There's a conditional equation. We can come up with rational, easy numbers. And we can say here, well, x could either equal negative 5 or x could equal 3. But unless x equals one of those, it don't work. Okay, does that make sense? Okay, so conditional equations, but identities always work. What you wrote down in your notes a moment ago, reciprocal identities. These are equations that will always work because, in a sense, they define they define each other. There's 3 more trigonometric ratios you need to know. The first one is called the cosecant. The cosecant. The cosecant is defined, it's abbreviated, by the way, CSC. You say, what? Well, normally we take the first 3 letters, right? But why can't we take the first 3 letters of cosecant?
Cosine.
Cosine already has COS, so we're going to go with CSC. The cosecant of theta is defined as the reciprocal of the sine. The cosecant of theta is defined as the reciprocal of the sine. The next trig ratio you need to know about is the secant. I see here cosecant and plain old secant, just like there's sine and cosine. Secant and cosecant. Secant, chanting S-E-C, S-E-C. Anyway, the secant of theta is defined as the reciprocal of the cosine. The secant is defined as the reciprocal of the cosine. And the last new trig ratio is the cotangent. And the cotangent, abbreviated COT, is the reciprocal of the tangent. It's how these ratios are defined. Now obviously if that's true, if cosecant is defined as the reciprocal of sine, then sine must be the reciprocal of cosecant. They are reciprocals of each other. Cosine and secant are reciprocals of each other. Tangent and cotangent are reciprocals of each other. That make sense? Well, that's how we define these different ratios. Well, if that's true, remember SOHCAHTOA, sine, cosine, and tangent. Well, in that case, sine's reciprocal cosecant must be the hypotenuse over the opposite. Since cosine's adjacent over hypotenuse, then secant must be hypotenuse over adjacent. Since tangent is opposite over adjacent, cotangent must be adjacent over opposite. Does that make sense? So there's really 6 trig ratios, but realize these are not unique. These are just reciprocals of ones we already identified. That's why sine, cosine, tangent are the big dogs. But these ones are simply reciprocals of the same. Look at page 11 in your textbooks, if you would, please. These are also sometimes called 6 trig functions. You might remember a function is an equation that produces only one answer. Well, when you ask for what's the sign, you're only going to get one answer. You can't get multiple answers for the sign. So it's also called a trig function. Trig ratios, trig functions. They give us this triangle here, and I'll talk through it quickly here, but I'll put it on the board for our YouTube audience. We've got the triangle A, B, C. We've got a side of 6, a side of 10, a side of 8. And we're focused specifically on the angle A. And the question is, what are the 6 trig ratios for angle A? Well, the way I like to list these out is I'll find the sine of angle A, the cosine of angle A, and the tangent of angle A. And next to these, I may list the cosecant, which is the reciprocal of sine, the secant, which is the reciprocal of cosine, and the cotangent, which is the reciprocal of tangent. Well, we memorized what saying, class? So sine is whatever what, class?
Opposite over hypotenuse.
All right, so for angle A, opposite
6
over hypotenuse, 10, 6 over 10, or 3 to 5. Well, if that's the sine, then the cosecant, which is the reciprocal, must be 5 to 3. It's easy. One extra step, but easy. Cosine, so SOHCAHTOA, cosine's whatever what? Adjacent over hypotenuse. So SOHCAHTOA. Okay, adjacent over hypotenuse. So adjacent,
8.
hypotenuse, 10, 8 to 10, or 5. What's the secant then? Since the secant is the reciprocal of cosine, 5 to 4. Easy enough. Tangent, TOA. Tangent's whatever what? Head off hand. Opposite over adjacent. What's the opposite? Adjacent. 6 to 8 reduces to 3 to 4. So therefore, the cotangent, which is the reciprocal of the tangent, must be 4 to 3. It's super easy as long as you memorize which is the reciprocal of which. All right? Here's how I remember it. In each pair, there's only one C word. Sine, plain old sine, is paired with the cosecant. Cosine is paired with plain old secant. And tangent and cotangent go together. So if that helps you, there's only one co in each pair, if that helps you to remember which one is which. Turn to page 12. Turn over to page 12. And take a look at number 1. Anyone remember what that Greek lowercase a is called? Alpha.
Oh, yeah.
Okay, so again, it kind of looks like an A, so remember that. You know, Jesus refers to himself as the Alpha and Omega, the beginning and the end. Alpha is the first letter of the Greek alphabet. But we're finding the sine, cosine, tangent, cosecant, secant, and cotangent of alpha. Again, it's awfully nice that then they gave us all 3 sides. Do they have to give us all 3 sides of the triangle? No. We could find the 3rd side ourselves, but don't let the gift horse in the mouth, as they say, whatever that means. And so for the sine of alpha, what would we get here, Jamie?
It'd be 3 to 5.
All right. So if we know the sine, Jamie, we also know the,
Reciprocal.
which is the
And cosecant.
Cosecant, which would be
5 to 3.
5 to 3. The cosine of alpha, Chris.
4 to 5.
4 to 5, and if we know the cosine's 4 to 5, we also know the
The secant
is
4 to 5. Or no, 5 to 4.
5 to 4. We can find the tangent of alpha, Quentin.
3 to 4.
3 to 4, and so we therefore know the cotangent must be
4 to 3.
4 to 3 because it's the reciprocal. Super easy? All right, at your seats, I want you to do number 6 on page 13. Now, funny looking Y thingy is actually a lowercase g. It's gamma. Okay? Gamma. It looks a little bit like a Y. It makes a g sound in Greek. Again, all of these lowercase Greek letters.
I'm writing them all down.
Finished? Okay, you're going to actually want to write that out.
Write that out?
Yes, you're going to want to write that out. Get used to writing it. Not just jotting down answers with no particular order, but writing it out. All right, so Ethan, what did you get for the sine of gamma?
21 over 25.
Good. Anyways, while we get the sine, let's also get class the cosecant, which is its reciprocal.
29 over 29.
Chris, what's the cosine of gamma?
20 over 29.
20 over 29. In class, once we get the cosine, let's immediately write down the secant, which is,
29 over 29.
and then let's go ahead and get the tangent of gamma, Jamie.
21 to 20.
21 to 20. And once we got the tangent, let's also get the reciprocal,
20 over 21.
which is the
Cotangent.
cotangent. Okay, so once you get the tangent, also get the
Cotangent.
cotangent, the reciprocal, which is 20 over 21. Easy enough?
Yeah.
All right, now flip back to page 11. Get your calculators ready. Because oftentimes, as we work, they won't give us all 3 sides. And sometimes the numbers won't work out nice, beautiful, and even whole numbers or integers. Sometimes, like we see in example 2, it's nasty. And so here we've got our triangle ABC, and we're given a side of 5.00 for side little a. Stand off to the side if you would please, sir. We've got a side of 14.0 for side little b. We don't know side C. But here's the deal. Once we get side C, we're going to need to use that number to help us find these different trig ratios. So we can't just find it and forget about it. We've got to find it and store it in the calculator's memory. Do we remember how to do that?
I don't think so.
Press store.
Store 1.
And then the button.
Yep, store 1, store 2,
How do
or
you
store
get
3.
it out of that?
How do you get it out of that?
How do you get it out of the storage?
Well, remember yesterday we said you could store a 0 and that would wipe it out. Or if you were trying to like, how do you find it again?
Yeah.
Recall, which is the RCL button right below the STO. All right, so at your seats, go ahead and find the length of the hypotenuse and store it in the memory.
How'd you get?
Right, checking your answer. Did you get the 14.866, blah, 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 blah? All right, go ahead and store it in the memory of your calculator.
I just got plain 14.
All right, so what do we have to do to find the hypotenuse?
You have to do 5 squared plus 14 squared and
Equals.
Yeah, 5.
You didn't do equals. And then take the square root. Because you did 5 squared plus 14 squared, and then when you hit the square root, it took the square root of 14 squared, which of course is 14. That's all. So make sure, just make sure you hit the equals. Go ahead and put this in the memory of your calculator. The 14.866. Blah, 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 blah. Okay? Any questions storing it? Are we all good storing it?
Mm-hmm.
Let me come check, make sure we've got it. So go ahead and recall the memory. There we go, good. Clear. Recall memory. So recall 1. There it is. Okay, good. All right. Make sure you're good. Recall 1, good, and recall 1, excellent. All right. So we're all good. Now Quentin is smart. Quentin's already put the fix on his calculator because he knows what's coming. We're going to need some trig ratios to 3 decimal places. So he's got his calculator fixed to 3 decimal places. Go ahead and do the same thing on yours. Good. Ethan's good to go. Jamie's good to go. And Chris is good to go. Can you show me like they did, please? Excellent. All right. So now we want to find, we're looking at angle A, correct? Angle B? Oh, they tricked me. All right, we're looking at angle B. We want the sine of angle B. Write this down in your paper, please. We want the cosine of angle B. We want the tangent of angle B. I'm going to change up the order a little bit with you here. Right below it, we want the cotangent of angle B. Right below that, we want the secant of angle B. And below that, the cosecant of angle B. Notice the order. Sine, cosine, tangent, cotangent, secant, cosecant. Sine, cosine. Tangent, cotangent. Secant, cosecant. But notice where your reciprocals are. Tangent and cotangent are reciprocals. Cosine and secant are reciprocals. Sine and cosecant are reciprocals, okay? So even in writing it out this way, there's a pattern. This is the way you'll see it on quizzes and tests listed out, is in this order. So let me get you used to this order now. All right, for sine of angle B, what over what, class?
Opposite over adjacent.
Opposite over hypotenuse. So katoa, opposite over hypotenuse. So the opposite is 14, and the hypotenuse is the memory value, right? So on your calculator, divide the 14 by the recall 1. 14.0, or just 14 divided by recall 1. What do we get?
0.942.
Good, it should round to 0.942. Now, while this is on your calculator, you realize when you come down to the cosecant class, you could do memory 1 divided by 14. But I'm too lazy for that. Let me show you on your calculator. This 1 over x button, it's right beside the pi button. Let me show the YouTube audience. See the 1 over x button? If you'll just push that button, it'll automatically give you the reciprocal of whatever's on your screen. So push the button, and now you've got the reciprocal. What's the cosecant? 1.062. So there's no reason to re-enter memory 1 divided by 14. You could. Go ahead and do it just for verification's sake, I suppose. Do recall 1 divided by 14. But again, why waste the time when a single button gives this to you? So you calculate the sine, hit the reciprocal button, you got the cosecant. All right, let's go to the cosine. Cosine's whatever what?
Adjacent over hypotenuse.
Adjacent over hypotenuse. Adjacent is?
5.
5 hypotenuse is?
Memory.
Memory. 5 divided by memory?
0.336.
0.336. And then what do we do to get the reciprocal?
Press the 1 dash x.
1 over x. That's one. It's a fraction bar, but 1 over x. Hit the 1 over x button. And the reciprocal of cosine, class, is? Yeah, but what is the reciprocal of cosine in general? Cosine's reciprocal is called the secant. So we're going to go down to the secant of angle B, and you said it was what again?
2.973.
2.973? All right. And then we're ready for the tangent. Tangent's whatever what?
Opposite.
What's the opposite?
14.
Adjacent?
5.
So we're going to do 14 over 5, which, I mean, it's rational. You could leave the 14 over 5, or you could plug it into the calculator and get
I'd rather not.
2.8.
I'm sorry, 2.800?
I'm lazy, I'm good.
If we do, well, here's what I was about to say. But my lazy says, well, let's just leave it as 14.5. But if you're going to make things decimals, do them all decimals. So there we go. Now, we know the cotangent's 5 to 14, but I'm not going to put that in the calculator. I'm going to hit the reciprocal button to get the cotangent. 0.357.
Isn't that a caliber?
Yeah, 357 Magnum.
Yeah. So I saw that, I was like, hold up.
Very similar to a 38 special, but more powder in the shell, more. Anyway, questions on this?
explosive.
Yes, questions on this. All right, we understand how to use the calculator. Reciprocal button, lifesaver, very nice. You're going to discover that in physics later this year. We'll do a lot with reciprocals and when we talk about light. And man, is that such a lifesaver. Memory, not having to recalculate everything over and over again. For instance, if you look at the book, they just kept entering the square root of 221 over and over again. Aren't you glad we didn't have to
I
do
wish I did that in
that?
chemistry,
We
though.
just use a memory. And so, yeah, so memory use,
I get rid of memory now.
reciprocal use, good. Yeah, at this point now, you don't need that number though in the memory, so store a 0. So put a 0 on the screen and store that in memory 1, and it's all good to go. Quentin's like, I already did that this year. Good job, Quentin. Show off. All right, questions on this. Your homework for this evening is to do page 12. Numbers 2 and 4. Those are going to use ratios, not decimals. Page 12, 2 and 4, use ratios, not decimals. Page 13, number 10. There you're using decimals. Page 12, 2 and 4, page 13, number 10. You're only doing the decimal calculator-y stuff on the number 10. You're not using the calculator for 2 or 4. Well, not for the ratios at least. All right, any questions on that? All right, well, when the bell rings, you'll be dismissed. Have a wonderful rest of your day.
Well, I